It's been a long time, right? Since last time we met each other. So, no, just a week. Right, I hope you visit the YouTube to see my lecture last time. So, in a video, we talk about one-dimensional dislocation, right? Okay, and then this is a summary. So one-dimensional defects, we call it dislocation. So the dislocation we introduce 3 types. The first one is called edge dislocation. Okay, the second edge dislocation is like this, right? And then if you get a force to this dislocation, the dislocation will move to the edge. That's why we call edge dislocation. And this is what we call screw dislocation. The second one is screw dislocation. You know, the lattice on the top layer and bottom layer split. So it looks like a screw from the top bottom, and do like kind of no, it's kind of screwing, right? Do you know what is screwdriver? Screwdriver, 螺丝起子, right? Screwdriver. Okay, so screw like this. Okay, so the mixed dislocation is the combination of the edge dislocation and screw dislocation. Okay, right, and then dislocation, there are 2 important parameters. The first one is called dislocation line. This is what we call dislocation line. We want to have a symbol like this, and then so you know this is called screw dislocation, this is edge dislocation. And then another one is the vector, the direction and what's the length of this dislocation. So this is called Berger's vector. So this is B is Berger's vector, right? B is Berger's vector. So you need to know this. The formation of dislocation, we also introduce this to you. And the edge, so the relationship between the dislocation with the property of mechanical property is that we call this plastic deformation, because once we make the dislocation, it cannot move, it cannot return back to the original position. So this is what we call plastic deformation. And today we are going to introduce another deformation, is called elastic deformation. That's what we're going to talk. But that will be the topic today. So dislocation is we also learn the slip system. Slip system is that, you know, when you do slip, this is also the one-dimensional dislocation. Is that you slip in the most dense plane, in the most dense direction. That's what we call slip system, right? Okay, so slip system is kind of mechanical deformation. So it's also important in the mechanical department engineering, mechanical engineering department, right? Okay, so this is what we learn about one-dimensional dislocation. Today, sections 4.6 is interfacial defects. Interfacial defects is two-dimensional dislocation. Two-dimensional defects. My mind is still in Japan. I'm sorry, I keep on making mistake. Okay. Anyway, forget about what I say. So the first one we are going to introduce you is external surfaces, and then grain boundaries, trim boundaries, and the miscellaneous interfacial defects. These are all two-dimensional defects. Okay, so let's take a look of this description. So if this is a cross-sectional image of crystal. So if you have a crystal, you cut it into half, and you see the cross-section of this crystal, And if you take a very close look with a microscope, which can reach to the atomic scale, you might see something like this. Okay, and then how can we define two-dimensional defects? The first one is called external surfaces. This is surfaces, external surfaces. Okay, and then this is internal surfaces. Okay, and you do see something missing here, right? Missing here. There's an atom miss. There's a one line atom miss here. Okay, so you know, how can we do this? Actually, this is like a toy. You can play with these toys. This is a stainless ball between two transparent plastic, and so you have you fix this into a. So this is a very small space, only allow one atoms in this in between these two plastics. So you can make something like this. So I have this for you here. I can show you this one. So this is what we call atomics. So you can see, as you can see, that there are two plastic, and there's a gap between two plastic, and you put a stainless ball here, right? So if you move around, you can see a lot of defects. It looks like this. Okay, this is atomics, right? So see that? No, you cannot. Actually, if you are interested in this, you are welcome to come to me after the lecture. Okay. So what I want to tell you is that this is called atomics, and you can see a lot of defects. You can create a lot of defects. Right, so I want to define what kind of defects you can see from this image. So this one, as you can see, this one is called gram, right? If you have this crystal, very pretty crystal here. This is what we call gram. A small single crystal, and this is big crystal if you compare to this one, right? Okay, and then you can see a line here, which is interfacial surface and ground boundary. Remember, we introduced you ground boundary before. So this is two-dimensional ground boundaries, and this is a place where the atom doesn't pack so well. So this is called amorphous region. Amorphous region. And then this is what we call atoms in the gas phase. You know, some atoms on the surface will be vaporized to the gas phase. Why? If you put these materials under a very high temperature environment, for example, it's going to go up to this boiling point of this material. So these atoms on the surface will be vaporized. Okay. So, and this is vacancy, zero-dimensional vacancy. Okay. And this is the external surface defects. This line here, all the atoms on the surface is external surface defects, because the atom doesn't bond very well compared to the atoms inside the material. Right? This is single crystal, and then atoms bond very well, but you have some bond missing on the surface for atom. Right? Right. So in your final exam, I might give you this picture, and I want you to tell me how many information you can get from this picture. So what you can do is you tell me what you can see from this picture. Like this, you tell me, oh, this is a gram, or this is a vacancy, this is a gram boundaries, this is amorphous, this is surface, etc. The more information you can give me, the more points you can get. Okay, so please remember this. So let's take a look of this, all of this one by one. external surfaces, the first one. So external surfaces is atoms has less coordination number, right? Because, for example, here if you have 4 coordination number, but here you only have 3, you have one direction mix to bond other atoms. You might have 2 mixing bonds, right? So less number of the bonds means it's more active. It's not stable. So the forming bonds are lower than the energy of the system. So the system here is higher. The energy of the atom here is high, lower than this one. This is high. So atoms is the surface having a relatively high energy state than the atoms in the matrix. So you have higher energy. That means you are not. It's not stable. It means that if you have higher energy, imply higher reactivity. So when you have a chemical reaction, the atoms on the surface always start to have chemical reaction with others, right? Not inside, because inside is very stable anyway. So like, good thing is that if you have a good reactivity, that means what? If this atom act as a catalyst, that means it's good, right? Because you want to reduce the activation energy. This is original reaction energy required. But if you have a catalyst, you can reduce the activity energy. So you have you save energy like so much like this, for example, right? So it's good. So this act as a catalyst, which is good. But for the bad thing is for corrosion, right? Surface is very easy to have it's very easy to oxidize, and the iron becomes iron oxide. So it's called corrosion, which is not good. So you have bad thing and you have a good thing. It depends on what kind of application. So external surface, one of the most obvious boundaries. Of course, everything you can see, you have external surfaces, right? So surface atoms are not bounded to the maximum numbers of the nearest neighbors. They are in a higher energy state than the atoms at in interior position. So higher energy state, right? However, because the surfaces, if you reduce the surface, you will have less reaction position. So to reduce this energy, materials tends to minimize if at all possible, right? So the total surface area. So you want to reduce the total surface area. What's the minimum surface areas for the objects? A sphere, right? A sphere. So a liquid assume a shape having a minimal areas. The droplet become spherical. So not possible with the solid. So this liquid try to tend to be a droplet which is spherical and minimize the energy, right? Okay, this is what we call what? 表面张力, right? Okay, so they want to bond very well. Okay, so next topic is internal surfaces. So there are many, as you can see, this is only one external surface. There are many internal surfaces. Okay, interfacial defects is that the boundary, the first one is boundary. Boundaries that have the two-dimensional and the normally separate regions of the materials that have different crystal structures and the crystallographic orientation. That's what all we know. So the boundaries can be described in terms of the dislocation arrays. Okay, so let's see that what kind of dislocation arrays. So first one is grand boundaries, twins boundaries, phase boundaries, and stacking force. So these are all regarded as interfacial defects. Okay. So first of all, let's take a look of the grand boundaries. We have learned grand boundaries before, because the grand boundary is the is inside the polycrystal, and there are many small single crystals get together, and the edge of the single crystal, that will be called ground boundaries, right? So as you can see, ground boundaries is small angle ground boundaries. This is the gram, right? Gram and ground boundaries here. So as you can see, so this is another one is called tiered boundaries. Tiered boundary is the edge dislocation arrays. I'm going to show you this very soon. Remember, this is edge dislocation, right? This is edge dislocation. And twins boundary is the arrays of the screw dislocation. This is screw dislocation, right? Button up, button up, button up, button up. This is screw. And the twins boundary is the arrays of the screw dislocation. So let's take a look at these three topics. So the first one, small or low angle ground boundaries. This is remember these figures. So this is the boundaries can be described in terms of the dislocation arrays. So this dislocation arrays here, two-dimensional, right? So for example, if this goes in this direction and this goes in this direction, you have an angle like this. Okay, this is called angle of misalignment. Okay, you have angle like this. However, if you take a look of the same different gram, this is gram A, this is gram B, compared to this host gram, and you have another direction, and then you have a small angle. As we remember, the big angle has a more higher diffusivity and mobility, right? Because you have more space in these gram boundaries. And of course, you might have higher reactivity, right? So these high angle gram boundaries, these low angle gram boundaries. Right. So the second topic is called tiered boundary. As you can see here, this is dislocation line, right? Dislocation line. But you have one dislocation line, two dislocation lines, three dislocation lines. This is what we call tiered boundaries. Actually, is the arrays of the edge dislocation, right? Arrays of the edge dislocation. So this type is called tiered boundaries. Okay. So, and then this is the angle of the misorientation. This angle. No Berger factor is here. Right. Okay. So this is called edge dislocation array. And we also call this tiered boundaries. How about twins boundaries? Twins boundary is the array of the screw dislocation. So why is, you remember this is screw dislocation is we split the top layer of often and bottom layer of often. So we split in one lattice spacing. And then if we split this layer and split this layer, split this layer, split this layer, this will be called arrays, right? So this is arrays of the screw dislocation. I'm sorry, I don't have pictures for you, but use your imagination. You split this layer, right? And you can split upper layer, bottom layer, and so you can make an array. So this is what we call twins boundaries. Okay, the boundaries between two catalysts. The boundary between two crystals that differ in orientation by only a few degrees, consisting of a series of the screw dislocations. Okay? So, how about the energy of this interfacial dislocation? Energy of interfacial defects. compared to the surface energy in the surface, interfacial defects will be lower or higher. Will be lower, right? Okay, so so for the surface energy, to reduce this energy, materials tend to minimize. We all know this. Okay, so interfacial boundaries and ground boundary energy is that the magnitude of the energy is a function of the degree of misorientations, being larger for higher angle boundaries. So, for example, this is a high angle ground boundaries. The energy of this boundary will be higher than this energy of this small angle ground boundaries. Why? Because this is more unstable, right? Because you have a bigger space, you have a higher mobility, you have a higher diffusivity, right? So the degree of the angle boundary higher, you got higher energy. It makes system most unstable. Okay, so the ground boundaries are more chemical reactive than the ground itself. So this place is more chemical reactive compared to this place. Okay, no problem. So if you have something, a foreign atoms going to this system, of course this will be the one easier to fill with impurities, right? So the ground boundaries can act as a trap for impurities. So impurities will be trapped in this place because there is a space. So you can have impurities, right? If this is atom A, you can have atom B here. Okay, so the impurity atoms often preferentially segregate along these boundaries, okay, because of their higher energy state. You can trap here. So impurity in brittle materials, the materials will fall at the ground boundaries. Okay. So if we talk about the polycrystalline and single crystal, normally we regard this as a same as a whole. So in spite of this disordered arrangements of the atoms and the lack of the regular bonding along the ground boundaries, a polycrystalline material is still very strong. So we regard this as strong as this. So the density of the polycrystalline specimen is virtually identical to that of the single crystal of the same materials, but not amorphous, because the space here, if we regard this as a big material, and it's almost the same in terms of the density, but not for the case of the amorphous materials. Okay? So now the important thing is that what we call ground boundary engineering. So if you make, this is a can of the Coca-Cola. Okay, for example, this is a can of Coca-Cola. And then you know this made of aluminum, right? This made of aluminum. So if you make a ground, this is not a single crystal. This is a polycrystal. And then how you can shape aluminum can like this? It was a pellet. And then if you have a pellet of aluminum, you push this a pellet of the aluminum, you push it, and to make it shape like this. Okay, so you need to have a very good design. How can you push this pellet and to shape the aluminum material looks like this? You cannot break this. You cannot have a hole this. You cannot deform of this. You need to make perfect of this aluminum can. And this is what we call ground boundary engineering. So what is this? So this is if a dislocation sliding in 1 grams, it was a rip through the entire materials. Okay, that is misregistry of the atoms at a ground boundary stop the dislocation, so it can act as a site for erasing dislocation. So if you want to have a dislocation, then you need to have a perfect crystal. Okay, but if you want to have a lot of defects, especially you have small gram defects, it's difficult for you to make a shape like this. So materials required is that if you want to have a high strength, not easy to slip. If you don't want to make something like this, if you want to have this material very strong, you need to have a very fine grain structures like this, because there are many spaces. And these spaces will stop to slip. Okay, so this material is not easy to slip, because you have a lot of small grains, and between small grains there are many spaces. So if you want to make this palette to become different shapes, it's difficult because you have many spaces to fill. On the other hand, this is called high strength, because you give a force to this material. This material will absorb the energy by what? By the grain boundaries. So you will have high strength. However, if you want to have a high ductility like this, you can make a tablet. You can make a palette like this. Then you need to have a coarse grain structure, which is a large grain diameter, like this. Why? Because you have less spaces. And if you don't have space, you can elongate these materials longer. So you can shape as you like. You can shape as you desire shapes. Okay? So this is called high ductility. So that's why you want to make the can, you need to design the crystal structure of the aluminum. Okay, so high ductility atoms sliding over atoms. This aluminum can like this. So I have a video for you to let you know how you make the aluminum can here. It's a very interesting. Let me see, do I have this or not? Okay, so if you make a different structure, you will get different result. Okay, so in order to make the can, you need to have a coarse structure. Coarse structure, rather than a very fine grain structure. Okay, if you make very fine grain structure, you cannot make a can like this. Okay, right. So next is the twin boundaries. What's twin boundary? This is what we call twin boundaries. Under the microscope, you can see a crystal lattice like this, and it looks like a mirror. You have a mirror here. You can see that the both sides show the same pattern. So a special type of a grain boundary is closed, which there is a specific mirrors lattice symmetry. Okay, so the grain of the materials between these boundaries is appropriately termed a twin. A twin. This 1, 2, right? It looks like a twin. Okay, how do we do that? Mechanical annealing. That's the things. Right. Others are miscellaneous interfacial defects. That's what we introduce, because we introduce grain boundaries, right? And arrays of the dislocation. Okay, tier dislocation, twins dislocation. And then now other possible interfacial defects. The first one we want to let you know is stacking faults. Remember stacking faults? BCC, FCC and HCP. FCC is the packing of A layer, B layer, C layer, A layer, B layer, C layer. Well, that's why we call ABC, ABC. HCP is A layer, B layer, A layer, B layer. So it looks like this: AB, AB, ABC, ABC. This is what? FCC. This is HCP. Another type is called phase boundaries. phase boundary is easy. You have phase 1 and phase 2. So between the phase, you have a boundary, right? This is what we call phase boundary. It can be solid, it can be solid liquid. Okay, and of course, this layer is more unstable compared to the in the inside of the layer A and layer B, or material A and material B. The final is called ferromagnetic domains. Ferromagnetic domains is that the boundaries that separates regions having the different directions of the magnetization is terms of the domain walls. So this is called domain walls. Actually, it's not really obvious, can be seen as space, but you have domains like this. Before the electrical field, before the magnetic field, the domain randomly distribute in the material. But once you apply a direction of the magnetic field, the domain will change the direction, right? To follow all the same directions. Okay, this is what we call magnetic domain walls. And this is another type of the defects. Okay? So how about energy? Defects and interfacial energies. So the interfacial energies is that the external surface area has the highest energy. And after that, after internal surfaces, that will be interfacial defects. Okay, so normally the interfacial energy will be greatest for the external surfaces and least for the domain walls. The domain wall will have least energy, and the internal surface has the highest energy, which is more unstable. Okay. So this is the summary of the two-dimensional defects. I will just introduce this to you. The key point is that I show you figures, and please let me know the information you can get from these figures. That will be in your, very likely to be in your final exam paper. Okay. Right. So before we talk about the bulk of